Hello, and welcome to Calculus Lesson 106. Now I'm sure that you've noticed that up to this point, we've only graphed functions where we have y equals some function of x. And we've kind of snuck in other notations there, like f of x equals this and whatnot. But it begs the question, what if there's a different function governing the x direction and the y direction? I was recently playing this video game with family where one person moves left and right and one person moves up and down, and your goal is to get to the exact middle point. It's really interesting because when you're doing everything right and someone else is doing everything wrong, it's almost impossible to get there. Anyways, today we are going to dive into parametric functions. That is, functions that instead of just having a nice clean definition of y equals blah, 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 we are going to define x as a function of t and y as a function of t, or time. So this is particularly useful if you think about physics. You often separate the x and y components. Y usually has to deal with gravity, x usually has to deal with wind or whatever else is pushing left and right. And so we graph functions that are parametrically defined. So usually x is a function of t or time, and y is a function of t or time. So let's look at this function here. So x equals t plus 2 and y equals 3t minus 1. Now, in order to graph this function, we unfortunately have to go back to the old school way of making a table. And generally, t starts at 0. So I'm going to write out a few points and then see what happens. So if t is 0, x is 2, y is negative 1. If t is 1, x is 3, 4, 5, and 6. That's easy. For y, when t is 1, I have 3 minus 1, which is 2. Then I have 5. Then I have 8. And then I have 11. Let's hope that that's right. Oh dear. No, that's not bad. Your book included negative t's as well, just in case it isn't time. Then we can simply graph this. So when I go negative 2 in x, I go down in y. When I go 3 in x, that seems wrong. Nope, that's fine. Sorry, positive 2. Whoa. 2, 3, 4, 5, 6. So when I go positive 2, I go down in 1. When I go positive 3, I go up 2 in y. When I go up to positive 4, I go up 5 in y. When I go to 5, I go up 8. And so on. And so it looks like this line there, and maybe I messed up this one just a little bit. Okay, so we can parametrically define and say this is t equals 0, this is t equals 1, this is t equals 2, and this is t equals 3. Now that's not really interesting, and you could actually just write that as y is a function of x, but we get some more interesting functions when we incorporate sines and cosines into our parametrically defined functions. Now, you might be wondering, can I do this on my calculator? Absolutely. There's instructions on page 546. The idea is that when you go into mode, instead of selecting y equals, you would select parametric. So I think it's PAR. You'll see that setting in there. And then when you go back to your y equals menu, it's going to have x equals and y equals options. So try that out. Pause the video, see if you can find it. Great job. All right, so let's graph this next one. X equals 2t and y equals t squared plus 1. Again, this will require us to make a table, time, or a t, x and y. T's will go this time from negative 1, 0 to 1. X, if I plug in negative 1, I get negative 2, 0, and 2. For y, I get t squared, which would be 1 plus 1, which is 2. 0 plus 1 is 1. 1 plus 1 is 2 again. If I go even further, because it feels like I need more information. If I plug in -2, I get -4 and 4. I get t squared, which is 4, 5. So this looks like, to me, a quadratic that has a y value of 1. So now I'm going to ignore the t's. I'm just going to look at 0, 1. I got -2, 2, and 2, 2, and then 4, and -4, 5. So it looks something like this. Okay? So you can graph parametric functions pretty easily. Now let's go to an interesting one. X equals cosine of t, and y equals sine of t. Since these are sines and cosines, I'm going to pick meaningful values of t. You're waiting for me to make a joke, aren't you? I know, it's coming. So let's do 0, pi over 2, pi, 3 pi over 2, and 2 pi. So for 0, cosine of 0 is 1, sine of 0 is 0. For pi over 2, cosine, sine. For pi, -1, 0. For 3 pi over 2, we have 0, -1, and then we have 1, 0 again. So what does this function look like? Well, at t equals 0, it's right here. At t equals pi over 2, it's up here. At t equals pi, it's down here. At t equals 3 pi over 2, it's down here. So it most likely looks like a circle. If you wanted to know for sure, you could plug it into your calculator, or you could plug in more points. So that does in fact make a circle. The last thing, since we're in calculus, and cool party tricks don't come for free, we have to figure out how to take the derivative of a parametric function. So let's take the derivative of the one that we just saw. So I want dy by dx. That's the derivative. Simple enough. But instead of being able to take the derivative of y with respect to x, I only have a derivative of y with respect to t. I really don't want to do the work to solve for t and then plug it in. That's just too much. So I can simply take the derivative with respect of y with respect to t and divide by the derivative of x with respect to t. The dt's go away and I'm left with what I had before. So what's the derivative of sine? That's cosine. What's the derivative of cosine? That is, oh dear, negative sine. So this is negative. Cosine over sine is cotangent of t. Now you do have a problem. That is, your slope is defined with respect to t, but at a given t, you can find the slope of that curve. So, for example, if we go back to our circle over here, if I wanted to find the slope at pi over 2, I would plug in pi over 2 here and find out that the slope is in fact 0. Does that work? Let's see. Yep, it does. Cosine of pi over 2 is 0. Sine is 1. So we get 0. Okay, if you try the other points as well, you guys can also get the derivative that way. And that is problem set 106, and that's the t.